So this is the take-up for the Unit 6 quiz. So first question here asks us to determine the vector, parametric, symmetric, and Cartesian equations of the line which passes through these 2 points. Okay, so I'm calling these 2 points A and B. So these first 3, I need a point and a direction vector. So I've got, a choice of 2 points. And in terms of a direction vector, well, it just needs to be parallel to the line. So if these 2 points are on the line, I can just connect A to B or B to A, or any vector parallel to that. So any scalar multiple. Okay, so your answer could look different to mine, but it represents the same line. Whereas with the Cartesian equation, we still need a point, all right? But we need a normal vector, all right? So I did what I said I was going to do here. I just connected points A and B to create this vector. So it's going to be parallel to the line, hence can be used as a direction vector. Now what I did here is I used that trick that we determined. Okay, I could have solved an equation to determine, any vector that was perpendicular to 7, -3, but I used the trick that we determined in class where you just switch the components and change the sign of one of them. So made sense for me to use 3, 7 instead of -3, -7, although that would have been perfectly reasonable. Okay, so for the vector, parametric, symmetric, it's just a matter of using my knowledge of the equations. So for the vector equation, it's the vector to the given point. I chose to use this one here. Perfectly fine if you chose to use that one there, plus my parameter, say t, times the direction vector, okay? And I should be specifying here that t can be any real number, okay? Because you can imagine that if you just want a segment of the line, you would say, t only between 0 and 5 or something like that. Now, just as a little heads up, you might be wondering, maybe I'm not using the letter t for any old reason. Anybody want to take a guess why we might be using the letter t here? Anybody want to give a go as to what that t might often represent?
Time.
Yeah, there you go. It's because it's going to represent time. So we think of moving along a line, and this will represent the time. Okay. Now, for parametric, it's just a matter of writing out the individual components, okay, as 2 separate equations. So 4 plus 7t, -8 plus -3t, okay? And then for symmetric form, it's just a matter of solving for t and equating the 2 equations, okay? But it's kind of nice to just not have to do that, to recognize that it's x minus the given x component, okay, y minus the given y component, okay? So again, I'm using this point here, okay? And in the denominator, I just have the components of the direction vector, okay? Now for the last one, I know that A and B now represents the normal vector, and then I have a particular point on the line, and hence I could just solve for the C value. Now, what's nice about the Cartesian equation is that there's one and only one, version of it. I mean, you could have, 6x plus 14y plus 88 equals 0, but then you could always reduce it into the nicest form, okay? That's one of the things. Oh, okay, does that, are my back? Okay, so we're back, so we'll hope that the recording will be okay. Okay, so the nice thing about the Cartesian form is that, there's kind of everybody should be getting the same answer, as opposed to here where your answers could look very different. All right, any questions on number 1? Okay, let's get to number 2. So here, it's a question of work. And what's interesting about this question is that you kind of have a combination of how the info is given to you. You have the force, where you're given geometric information, okay? And then for the displacement, you're given the you're given algebraic information. Okay, but the idea is realizing that because the force is not given in an algebraic way, you're probably going to be working with the geometric version of the work formula. Okay, so the first thing I did here is I calculated all the information or wrote down all the information I have. So they give me the work outright. All right, they give me the magnitude of the force outright. And then what I could do is calculate the displacement vector because I'm going from one point to another. So I just subtract in order to get the displacement. And then from there, I can calculate its magnitude. So what this gives me is everything in my work equation except for the angle. And of course, that's what I'm looking for. All right, so I calculate the angle and there we go. Nothing too complicated here. It's just, dependent on what information I was given. All right, any questions on this one here? Okay, let's move on to number 3. So number 3 says determine the area of the triangle formed by these two vectors placed tail to tail. Okay, and this is where we have to recognize that there was a nice geometric meaning for the magnitude of the cross product. That if I take the cross product of two vectors tail to tail, it gives me the area of the parallelogram formed by the two vectors. And so the area of the triangle would just be half of that. All right. So this is what I'm trying to solve, is the area of the parallelogram divided by 2. And the area of the parallelogram is given by finding the magnitude of the cross product. So the first thing I have to do is find the cross product of these two vectors. So again, hopefully everybody has found some trick to help them easily determine the cross product. All right. So once I have that, I can find the magnitude, and in this case here, determine the area of the triangle. Okay, either in exact form or as an approximation. All right, any questions related to this one here? Okay, so it's just one of those things that, now we know gives us a nice geometric interpretation of this operation. All right, let's move to number 4. So here I'm asking you to prove this this identity. Essentially, it's an identity. So can somebody tell me what the first step is going to be? And I look at my left-hand side, and this left-hand side definitely looks more complex than the right-hand side. So that's why I'm going to work with this one here. And there was, I think in the homework, you probably had a couple of these, and they often, use the same tricks. Okay. And this one needs a particular trick to start it off. Okay. What is that trick? How do we recognize the square of the magnitude of a vector? Okay. What special property of one of our operations involves the square of the magnitude of a vector? Can somebody start me out on this one here?
The dot product.
There you go. It's one of those dot product characteristics that if I dot a vector with itself, it's equal to the square of the magnitude. Okay, so that starts me off here, as I can rewrite the magnitude of u plus v squared as u plus v dotted with itself. All right, that when I dot a vector with itself, it's equal to the magnitude squared. And lo and behold, what do I have in the second expression? Something very similar. Okay, but what this does now is it brings me to an expression for which I can do a heck of a lot of algebra. Okay, so the first thing I can do here is use my distributive property and my commutative property, okay, to simplify both of these two. Okay, now you'll notice here that I, skipped a step that I would often write, because when I have u.v and v.u, I recognize that, dot product is commutative. So that just gives me 2 times u dot v, okay? And we notice that I get something very similar in the second expression, except now I have the minus 2u dot v, which cancels out with that one there. And lo and behold, you know, hey, u dot u, magnitude squared. Another u dot u, that's another magnitude of u squared. That's where the 2 times magnitude of u squared comes from, and then similar for the v's, okay? And we get exactly the right-hand side, okay? So again, this is about, you know, being able to prove this. As with a lot of our proofs, is we use previously determined laws or rules. So whether it's, you know, proving a trig identity using other trig identities, here it's about using all these characteristics of the dot product. Okay, and there's a whole bunch of these different identities. You know, if you look in the textbook, I probably gave you a couple, but there's a whole bunch in there that you could prove. All right, any questions on this one here before I move on? Okay, this, you know, is kind of one of our, this is, I would say, more interesting, one of the more interesting questions, perhaps the only really interesting question in this quiz. No? Okay, so let's move on to number 5. So here, determine vector and scalar projections. So nothing fancy about vector and scalar projections, except now I'm asking you to find a projection onto a line. What do we normally project a vector onto? What do we have a formula for? We project a vector onto what kind of object? Can anybody tell me what I project a vector onto? Another vector, okay? So essentially, in order to use that machinery that we established with respect to projections, I'm going to have to find a vector that represents the direction of the line. And well, what would be a really good, representative for a vector that represents the same direction as a line? So not the given point, because again, we can't be, yeah, so we can't be projecting onto a line, but, you know, similarly is that we have in here, we've got a direction vector which represents. So I actually drew a little, made up a little diagram here that if this is my line, okay, I'm going to use my direction vector representing the direction of the line, okay? So that now I can, you know, find my shadow onto the line, and I can find a vector and scalar projection. So in this case here, you know, I did it so that I first just found the scalar projection, okay, of u onto m, and I used my formula for scalar projection. Now for the vector projection, there was no point in redoing some of this work. Okay, there was no point in using the formula. Had you started from scratch and used the formula that we came up with for the vector projection, no problem, you would have gotten the same answer. But here I made use of the fact that I've already found the scalar projection, and I'm just multiplying that by the unit vector in the direction of m, which is what this represents. Okay, so my scalar projection times the unit vector in the direction of m, which of course is just the vector divided by its magnitude. And then I just, you know, you really, it is good form to write out the actual vector as it's written here instead of writing it as a scalar multiple. Okay, so again, this one actually was a bit interesting because, you know, this idea that I had to determine the, you know, to think of using the direction vector as a representative for the line or the direction of the line here. Okay, so any questions on this one here? Okay, so we'll move to the last question. All right, and this one was a little more straightforward. Determine the angle between these two lines. Now this is kind of nice because the lines are both given in the same form, so I don't have to make any changes here. So since they're given in Cartesian form, I might as well use the normal vectors, okay? So what we saw was that we determined that the angle between the normal vectors is equivalent to the angle between the two lines, okay? So naturally, I'm going to use the dot product to determine that angle, okay? That n1 dot n2 is equal to the geometric definition. So on the left, I use the algebraic definition. On the right, I work with the geometric one, and the only thing I'm left with is the angle. But when you have two lines, okay, if we remember, when you've got two lines, there's actually two angles between them. There's an acute one and there's an obtuse one. And the standard is to always use the acute one to represent the angle between them. So if you do end up coming up with an obtuse angle, what technically represents the angle between the lines is the supplementary angle, okay? So I'd have to subtract from 180 to get what we officially refer to as the angle between these two lines. All right? So are there any last questions on any of these problems? Okay, so we are good. We'll see each other Monday morning for the rest of our lessons. All right, take care, everybody. We'll see you soon. Yeah, thank you all for coming. Okay, so let's just take a look here. You're talking about number 5. Number 5. Yeah. So yeah, Samya, what did you want to ask about number 5? Number 5.
So I'm just a little unclear about like the whole line development like formula. I don't think I've fully kind of understood like the lesson. So in this case here, why is the z value equal to 0 for the direction vector?
Okay, this likely, I don't know if we probably didn't deal with it in the lesson. I think this should have come up in the homework. So when you have symmetric form, okay, let's say the z component of your direction vector is 0, okay? So in this case here, it's the writing's going to look awful, but I'll do the best that I can. So if you've got, so now I know that my point is 5, a -1, 5, okay? So let's say I've got a, that's supposed to be a bracket there. Let's say I've got a line that passes through this point and has this direction vector. Okay, so let me look just at the z component. So if I were to write it in parametric form, I have z is equal to, well, 5 plus 0t. Well, wait a minute. What does that give you? That just gives you x equals 5. Can you solve for t in this scenario? And the answer is no. There's no t to solve for. So when we put it in symmetric form and one of the components of our direction vector is 0, we just write it as, in this case, here's z equals 5. So when you see just z equals 5, or if you see x equals 1, it means that the z or x component of that direction vector is 0. Okay? Does that clear it up, Samya? Samya? Oh, sorry. Unfortunately, I'm not hearing you well. Maybe you can type it into the...
I got that. I'm just...
Samya, you're going in and out. Can you type it in the chat instead? You keep going in and out, so I'm not hearing what you're saying. So in this case, did you say that the point is just on the line? Well, the point that's on the line, which I don't need to use, would be 5, -1, and 5. but I never need to use the point on the line. What I need to use is I need to take this vector u, okay, and I want to project it onto this line. But the formulas that I have are projecting a vector onto another vector. So I need a vector that represents the direction of this line. And a perfect candidate for a vector that has the same direction as the line is the direction vector, okay? So not the point on the line, but the direction vector, which is parallel to the line, okay? Because this vector here, you know, this is my vector m, okay, is parallel to the line. So what I do is I can place that in where I like. So I can project this vector on to the direction vector. So what will it produce? You know, it will produce, you know, when I do the projection, it's going to produce that shadow onto this line. Okay, does that make a bit more sense?
Yeah. So like when we say the general form of like the equation of the line, we say we have just one point and then you have the direction vector times t, right?
Yeah, so that's...
So the 5, negative 1, 5, you said, is that a point or is that the direction vector that
okay,
you were
so
talking
remember,
about?
this is the point. Okay, so when you look at the look at the format of the symmetric form of the line, is the numbers that are subtracting the x, y, and z components. Those are your that represents the point on the line, and the denominators represent the direction vector. Okay.
Right.
So if you go back, so for example, if I have, say, in this example here, let me use one where the value is not t, not 0. So let's say I have, you know, x is equal to, what would we have? 5 plus 3t. Remember how we get...
okay, I see what you're talking about.
Yeah.
Okay.
We solve for t. So the number that subtracts x is the component of the point. And then what we divide by is the x component of the direction vector. So the direction vector is found in the denominator. The point is found in the numerator.
Okay. So in this case, you wouldn't just include it. Direct. You'd have to write it entirely as like a separate statement with the semicolon, right? In the case that you don't have a t value, or for the...
Yeah, in this case here, you recognize that as meaning that the z component of the direction vector is equal to 0. That's exactly it.
Right.
Okay.
Yeah. Thank you.
Okay, great.